NASA has recently revealed some eerie cosmic sounds that go against the popular misconception about the muteness of space. This discovery proves once again that the universe is far from silent. The revelation came from the Perseus galaxy cluster, located 250 million light-years away from Earth. There, NASA uncovered an otherworldly howling coming from the supermassive black hole at its center. This discovery isn't super fresh. It was made in 2003. It marked the first time scientists detected an acoustic phenomenon from such a distant source. Sadly, the sound was not something you would be able to hear. Its frequency was just too low for the human ear to register. The lowest pitch the human ear can perceive is 20 Hz, 20 cycles per second, but the sound emitted by the black hole is a B-flat, 57 octaves below middle C, with a frequency of 10 million years. But NASA brought it into the realm of human hearing in 2022, turning that invisible sound into something you could actually experience. It was a breakthrough of cosmic proportions when NASA revealed that sound waves could travel through space, specifically through the medium of the Perseus galaxy cluster. This medium is a hot, dense gas, something far more substantial than the empty vacuum between galaxies. That's how sound waves manage to travel there. Those waves, produced by the supermassive black hole at the center of Perseus, resonate through the hot gas as ripples. It's like how sound travels through water here on Earth. The thing is, space is indeed a vacuum, which means that sound cannot travel through it in the traditional sense, but the gas surrounding the black hole in Perseus provided the perfect environment for sound to travel. The black hole's powerful jets create ripples, sending vibrations through the gas, and NASA scientists have identified those vibrations as a type of cosmic sound. Previously, it was totally invisible and unhearable, but now, for the first time, astronomers have helped it to take a form humans can hear. To give us a sense of how deep this sound is, NASA raised its pitch by 57 octaves so that it could finally be audible to the human ear. The result is a haunting, bass-heavy hum. It feels as though it is resonating from the very core of space itself. What NASA did is called sonification. This process involves mapping the characteristics of the data to audible sound. As a result, we can experience something that is otherwise beyond our perception. See those brighter areas of the cluster? They produce louder and higher pitched tones. The sonification of the Perseus black hole isn't just a scientific discovery. It has allowed us to see, or should I say hear, the universe in a completely different way. NASA has used this technique on several different space objects, including stars, nebulae, and galaxies, giving us a glimpse into the various ways space can sound. One of the coolest NASA's sonifications is Cassiopeia A. It's the remains of a star spotted as a supernova more than 300 years ago. Located around 10,000 light-years away from Earth, this shattered remnant of a once massive star has a neutron star at its core, and it's the youngest neutron star in our galaxy that we know about. To perform the sonification of Cassiopeia A, NASA took the data captured by the Chandra X-ray Observatory and translated it into sound. Starting at the center, a triangle-shaped tone marks the location of the neutron star. Then, the sound spreads outward, which represents the expanding debris field. That's when the pitch rises and the tones become brighter. The sound grows louder and seems to mirror the outbursts of the supernova and the formation of new elements. The Tarantula Nebula, located in the Large Magellanic Cloud, is a hotbed of star formation and one of the most active regions in the universe. Astronomers have been studying this nebula for a long time to learn more about how stars are born and evolve. So, no wonder that NASA scientists have been doing their best to translate the data from the nebula into sound. They've been mapping brightness and pitch to various features in the nebula. So, airy synthesizer-like tones represent the chaotic and hot gases surrounding the most massive stars. And the cooler gases that are forming new stars have soft, low notes. Piano-like tones correspond to the brightest stars, and the central cluster of stars sounds like a rain stick. Interestingly, NASA's investigation into the sounds of space doesn't just involve cosmic phenomena. It's also based on the experiences of astronauts, and some of them are truly eerie. After all, space exploration is always filled with unexpected surprises, and sometimes those surprises come in the form of strange noises aboard spacecraft. One such incident occurred aboard the International Space Station when astronaut Butch Wilmore reported hearing a strange noise coming from Boeing's Starliner spacecraft. By that time, this spaceship had been docked at the station for almost 3 months. The Starliner had just completed an 8-day mission that went awry, and technical issues had been plaguing the spacecraft ever since. Wilmore described the sound as a pulsing noise, similar to a sonar ping. It was coming through the spacecraft's speaker system. This strange noise made Wilmore contact NASA's Johnson Space Center in Houston. Of course, Mission Control immediately began investigating. They were able to listen to the audio inside the Starliner. Wilmore even held his microphone up to the speaker so that NASA could hear it more clearly. The people in charge of the investigation finally identified the source of the noise. They announced there was an audio configuration issue within the ISS's complex communication system. The thing is, this system connects numerous spacecraft and modules, and such configurations can sometimes lead to strange noises. NASA reassured everyone that such an issue wasn't really unusual. At the same time, they encourage astronauts to report any unexpected sounds they come across. At the same time, this incident was just another proof of how tricky it is to maintain advanced spacecraft systems in orbit. The Starliner had already faced serious delays and setbacks, and every new issue added extra pressure. Everyone was worried about the spacecraft's safe return to Earth. In any case, it's not the only incident involving eerie space sounds. In 1969, during the Apollo 10 mission, astronauts heard something truly bizarre while orbiting the moon. Now, Apollo 10 was a dry run for the historic Apollo 11 moon landing. This mission involved astronauts Thomas Stafford, John Young, and Eugene Cernan. They were testing the systems of the lunar module. Everything was going smoothly. And then, they started passing behind the moon. In that region, radio signals from Earth couldn't reach them. At that point, they all started hearing a strange, high-pitched whistling sound. It was coming through their headsets. The origin of this noise baffled the astronauts, since it wasn't supposed to exist in the near vacuum of space. At first, they simply joked that it sounded like outer space music. But in reality, the situation was quite unnerving. The astronauts were on the dark side of the moon, far away from Earth and any help. And now, there was also that eerie, mysterious sound they couldn't explain. At the time, NASA was super worried about astronauts' health and mental condition. So, the crew didn't immediately report the noise to Mission Control. But after they returned to Earth, NASA engineers thoroughly investigated the phenomenon. They came to the conclusion that the sound had most likely come from the spacecraft's communications system. The reason could be the unusual circumstances of the mission. After all, the spacecraft was kinda cut off Earth. The moon was between it and our planet. Still, even after this extensive analysis, the origin and nature of the whistle is still a great mystery for many people. Anyway, all these new discoveries and old cosmic puzzles prove that the universe is far from silent. It hums, roars, whispers, and reveals the mysteries of the cosmos one note at a time. In the future, as our technological abilities continue to evolve, NASA's work with sonification and its study of strange astronaut experiences will likely lead to even more awesome discoveries. And if we listen more closely, we may find that the universe is much more talkative than we think. If you were floating in space, no one would be able to hear you whisper, talk, or even scream in horror. At at seeing a giant asteroid coming towards you. It's not only that you'd be far away from Earth, but sound needs space to travel through. Sounds are just vibrations of molecules and atoms in some medium, like water or air. Your body will pick up sound waves through the ear canal and to the eardrum. Vibrations we receive then transform into electrical signals so our brain can understand and recognize them. Frequencies of sounds humans can hear are between 20 to 20,000 hertz. Sound travels 4 times faster in water because molecules are closer together than in air. Naturally, it travels faster through steel than both water and air. The loudest natural sound on our planet is one made by an erupting volcano. Not 100% certain, but scientists believe the eruption of Krakatoa in 1883 was probably the loudest sound humankind ever had a chance to hear. It exploded with enormous force, destroyed its island, and released 20 million tons of sulfur into the atmosphere. People even heard it 3,000 miles away. It would be like someone producing a sound in New York, and people hearing it all the way in Ireland. Sound can take many forms, but humans are most familiar with it in the form of pressure waves that move through the air. Sound goes more slowly through heavy gases and colder air. It travels faster through lighter gases, for example, helium. There's no water or air in space, so the sound that doesn't have anything to travel through. Our atmosphere consists of 10 trillion atoms, which is like dense soup creating a way for sound to travel. And there are only 10 atoms per cubic meter up in space. That means space is empty and silent. But it wasn't always like that. The universe is 10 to 20 billion years old. It appeared as a result of the Big Bang. It wasn't an explosion that started from just one single point, but rather space appearing everywhere in the universe at the same time. Back then, the whole universe was like a hot ball of plasma. It was much thicker than today, so the sound could pass through it. As the universe was forming, it produced shock waves, and they, in their turn, produced a cosmic rumble, way deeper than things our ears can normally detect. These are the actual and the first sounds the universe ever produced, at the stage when it was still forming. Scientists decoded them and pitched them up to a version we can actually hear. As time went by, the universe was stretching. Today, it's a lot wider, emptier, and quieter. It's good for us, though. If sound traveled through space with ease, we would constantly hear loud explosions, crackles, moans, and other sounds space bodies make out there. The sun isn't silent either. Here's the sound of its vibrations created by its loops, waves, eruptions, and other activity. The sun creates trillions and trillions of watts of sound energy, something like pulsation, low heartbeat. It helps researchers discover what's going on inside of the sun and understand its layers. If it wasn't muted for us on Earth by the lack of air in space, it would be like hearing a jackhammer all the time. If you and your friend were taking a walk on the surface of the moon, you wouldn't be able to hear each other talk. No air, no sound. But that doesn't mean the moon itself doesn't produce any sound. When the first spacecraft landed on the moon, it caused crashes which later led to moonquakes. Scientists took a chance to measure vibrations going through the moon to figure its internal structure. They realized they caused vibrations that lasted longer than they expected. Any similar vibrations on Earth? It was like those moonquakes were producing the sound of a ringing bell. When we have earthquakes, moisture in the ground acts like a sponge. It absorbs the energy of the waves spreading around until it ends their effects, which is why water eventually stops the earthquake. The moon is dry, more like a solid rock. Moonquakes are less intense, but there's no water to stop them, so vibrations just go back and forth through the moon. The solid rock stops them at some point, which is when the ringing stops too. Let's see what happens with the sound on different planets. Neptune, Uranus, and Saturn are mostly made of helium and hydrogen. These gases are way lighter than the atmosphere on our planet, so your voice there would generally come out in a higher pitch. But each planet has its layers that make differences in sound. Neptune has its murky depths, Uranus its methane clouds, but they're both freezing, made of gas, and have ice particles in their atmosphere. Saturn, also a gas giant, boasts wild, raging storms. Saturn's biggest moon Titan is the only one known for having a real atmosphere. It's thicker than the one we have on Earth. It's very cold there, and it rains liquid methane. In 2005, researchers sent the Huygens spacecraft that managed to record incredible audio you might find familiar, the sound of the winds, but billions of miles away from us, on Titan itself. If you were there, you might even hear the sound that reminds of a waterfall, while, in reality, it's flowing, liquid methane. Moving to Jupiter. It doesn't have a solid surface either. It's made of gas that becomes denser the deeper you go. At some point, it even turns into a liquid. The sound is different in each of those layers. Jupiter is actually pretty noisy and has bizarre sounds. It creates intense radio storms with powerful lightning bolts. While there, you'd hear their echoes of echoes, just going back and forth. Mars. Its atmosphere is way thinner than Earth's, which means there are not many molecules for sound to travel. Winds can get pretty fast, like our hurricanes, but on Mars, they would feel like a gentle breeze. You wouldn't necessarily hear the storm, though. You'd maybe hear the dust as it gets picked up and banged against your spacesuit. In the thin atmosphere, your voice would be much quieter, and it wouldn't travel far. Someone could be standing next to you and screaming, and you'd probably hear nothing. Low-density air usually makes our voices sound higher-pitched, but the cold temperatures, like on Mars, slow down the sound so it would balance out again. Your voice there would sound a bit distant and blurry, and imagine listening to an instrument like a guitar or piano there, like some muffled melody from a dream. Sound on Venus is kinda the opposite of Mars. Venus has a dense atmosphere, much denser than ours, something between water and air. There, you'd hear sounds like when you're underwater. The environment is a bit different with 900 AF, 482 C, and 100 tons of atmospheric pressure, but let's say you have a magical spacesuit that protects you from getting crushed or scorched. While on Venus, you'd hear thunder. 40 years ago, a spacecraft successfully landed on its surface and managed to go almost an hour before it shut down. It picked these amazing sounds of strong winds. If you started talking on Venus, your voice would first hit the lower pitch because of the dense atmosphere, but it would then sound higher because hot air increases the speed of sound. It would all be kind of distorted and muffled together with the sounds of thunder around you. Mercury is a rocky body with no atmosphere, so standing on its surface and talking would be like trying to talk while floating in space. Useless. Those are almost vacuum conditions, which would make you think Mercury has no sounds at all. Still, you can hear them, though not in the air. The rocks. Put your ear against the ground. Maybe a Mercury quake is coming. The universe is a place connected by light. Light can go anywhere from any spot in space, but not the sound. So, not only do we have a planet that supports life, but offers a wide palette of sounds. Even without us, it wouldn't be a quiet spot. A light breeze gently caressing treetops, earthquakes, volcanoes, deserts. The ocean with its waves on the surface and scary sounds deep below. Up there, it's a quiet mystery, but down here is true magic. Did you know that there's an astronomical object in which space and time actually swap places? How does it work? And what exactly does swapping space and time mean? Well, let's figure it out. Imagine that you're on a spacecraft. The vehicle can only move straight. Your path leads to some inevitable point, and you have no idea what lies ahead. You can only hope that it won't be too bad. Meanwhile, everything around you is complete madness. A chaotic collage of many historical events. What do you see? Ancient humans and dinosaurs. The birth of the universe? Future? Who knows? That's what the universe would look like if we swapped time and space. And theoretically, this is what you'd see if you fell into a black hole and somehow were able to survive. But how is something like this even possible? First of all, let's discuss time and space. Imagine drawing a light bulb on a sheet of paper. Then grab one more sheet and draw how it lit up. Right now, it's just a small circle of light. Another sheet. The circle of light is growing. It gets bigger and bigger in size until finally it turns into a huge circle. In real life, the bulb lights up in the blink of an eye. That's because the speed of light is the fastest in the universe. But here, on our drawings, we captured the propagation of light frame by frame. We see how over time the light has grown from a small dot to a large circle. But if you connect these circles, doesn't it remind you of some shape? For example, a cone? Yes, exactly. This is called a light cone. And time is the central axis of this cone. Why? Because light turns from a small dot into a large circle over time. To remember it, let's draw a time vector, an arrow inside the cone. It goes from the past to the future. Meanwhile, the circles are space. In space, we can move however we want, in any direction. We can move up or down, in zigzags, and so on. But no matter what zigzags we draw along the timeline, we're always moving forward. We can't turn back time, and we can't stop it. This helps us define time and space. Time is the direction in which the light cone is oriented. This is the direction where all our paths lead and where our future inevitably lies. And space is the whole variety of directions perpendicular to the timeline. This is a straightforward graph. If it could be applied to the entire universe, then time would flow the same everywhere. However, if you've watched at least some popular sci-fi movies, you know that this isn't the case. In reality, time can be crazy. For example, if you're chilling near a black hole, what will be 2 hours for you may turn out to be 20 years for your friend on Earth. But why? Take a deep breath. Now, gravity comes into play. Oh, I know about gravity. It's that thing that helps me to stand on the ground, you may think. But it's much, much more complicated than that. Gravity is one of the basic physical forces in our world, and it's incredibly powerful. In fact, she's such a girl boss that she can distort space and time. She literally can influence the speed of time like an almighty wizard. How? Well, let's take something slightly bigger than a light bulb. For example, a supernova. Somewhere in the universe, a star has just made a boom. How do we know about it? Well, nothing in the universe, no sound, no radio waves, nothing travels faster than light. So we'll know about the birth of a supernova only when we see it. And this will happen only when its light cone grows enough and reaches our planet. So the light cone grows and grows. So far, everything is fine. And finally, it reaches our planet. But there's a catch. You see, our planet is massive. Very massive, and it has pretty strong gravity. What happens then? Gravity changes the direction of the light cone. It begins to attract the cone to the center of our planet, and with it, it also attracts our arrow of time. That means it slows the time down, and the closer the light cone is to us, the more the arrow bends, and the slower time goes. What does it mean? For example, the fact that the watch on your ankle will lag behind the watch on your wrist, that your head is aging faster than your legs, and that astronauts in Earth's orbit age a little slower than people on Earth. This is what scientists call general relativity, right? But how does this relate to our topic? How can we understand what will happen if we swap space and time? Don't worry, we're almost there. Now imagine a cosmic body with incredibly strong gravity. It bends time and space so much that it feels like they swap. This is a black hole. A black hole attracts absolutely everything to its center. No stars, planets, no light can escape from there. Let's say our light cone is approaching it. First, as usual, time begins to bend towards the center of the black hole, attracted by its gravity. But the gravity is very strong, so it bends more and more. and time goes slower and slower the closer you're to the center. In the end, the light cone crosses the boundary of the black hole, the so-called event horizon. At this point, it got so distorted that now it's literally pointing downwards. We can say that time has changed its direction. Time is pointing downwards? What kind of nonsense is that, you may ask? It will be easier to explain in a real example. Imagine you're a crazy astronaut who decided to jump into a black hole, and there's an observer in a spaceship who watches you doing this for some reason. At first for you, nothing changes. You look at your watch, you see that 5 minutes have passed, and everything is okay. But for the observer, first of all, you'll fall for a very long time. The observer has been sitting there for 50 years, and you're still falling. All because your time has slowed down. Secondly, since space is also distorted near the black hole, the observer will see how you'll begin to stretch like spaghetti. This is a scientific term, by the way. It's called spaghettification. And then, you finally cross the event horizon. The observer doesn't see you anymore. Light cannot escape from a black hole, so your image won't reach the observer, even if you're still inside. And what about you? What if you somehow survived? Remember, the time arrow is pointing to the center of the black hole. What does it mean? It means that now, the center of the black hole is your future. It isn't a place. It's a fate that you can't change. And wherever you came from, as well as the rest of the universe, no longer exists for you. Because now it's not a place, but an event from the past. And since you can't turn back time, you'll never be able to come back. But what is around you? Complete chaos. The rays of light now move in all directions, forward, backward, and so on. The rays depicting the events of the past, the future, the present, all this is moving around you. In reality, space and time didn't swap places, but it feels like they did, because in space, you can now only move forward as if along a straight line, and time, reflected in the light rays, surrounds you everywhere and moves in all possible directions. And here we go back to the beginning. This horrifying example helps us imagine what it would feel like if time and space got reversed. Of course, all this is just theories and guesses. The very idea that we're moving in some one direction, the one we haven't chosen, and there's complete time chaos around, sounds quite frightening. And yet, it would be a very interesting experience. Sounds dangerous. You go first. Imagine a being so powerful, it can suck in entire galaxies, so mysterious, it's invisible to the naked eye, and so impressive, it bends the very fabric of space and time to its will. Yes, meet my mother. Just kidding. Actually, meet the ultimate superhero of the universe, the black hole star. What is it, and how does it work? The universe is full of marvels, and the black hole star is one of the most impressive ones. It's a supermassive force that can bend the laws of physics, and a true enigma for scientists to unravel. No wonder science fiction writers find them so captivating. A black hole star, also known as a quasi-star, is a hypothetical type of extremely massive and luminous star that may have existed early in the history of the universe. They're predicted to be as luminous as a small galaxy, but unlike modern stars, they weren't powered by nuclear fusion in their cores. A quasi-star's energy would come from material falling into a black hole at its core. And yes, just like a normal black hole, these stars have the power to suck in anything and everything that gets too close, including stars, dust, and even entire galaxies. But how is it possible that the star is born from a black hole? And what's more, how do they continue to coexist together? Well, first, let's discuss how black holes are born in general. It all starts with a supermassive star, one that is at least a few times more massive than our own sun. This giant of a star burns bright and hot, shining with the light of 1,000,000 suns. But eventually, it runs out of fuel and its fate is sealed. As its lifespan comes to an end, it makes one final, massive boom. A blast so powerful it can outshine an entire galaxy. This blast is called supernovae. During this boom, the outer layers of the star fly away while the core gets squished together by its own gravity. If the squished core is heavy enough, it can keep squishing until it becomes a black hole. And just like that, a black hole is born. Don't even try to put diapers on this thing. Now, this cosmic monster baby can continue to grow by swallowing up anything that gets too close, including stars, dust, and even entire galaxies. This is basically what's happening now in our universe, with supermassive stars. But what about quasi-stars? The formation of a quasi-star could only happen early in the development of the universe, before hydrogen and helium were contaminated by heavier elements. And because of that, quasi-stars have one important feature. They are gigantic. They may have been dwarfing even the largest known modern stars like VY Canis Majoris and Stephenson 218. No wonder they're so scary. They were born from protostars, one of the first stars in the universe, the great-great-grandfathers of, you know, everything. So now imagine a protostar so massive that its core collapses into a black hole, just like we described before. But the key difference is that in a regular supernovae, the outer layers of the star are blown away by the energy released during the boom. Meanwhile, in a quasi-star, these outer layers are massive enough to absorb the energy without being blown away. What do we get in the end? A star with a black hole in its core that weighs from 1,000 to 10,000 solar masses. This quasi-star is about 14,000 times bigger than our Sun, which makes them bigger than any star we know today. Once a black hole is formed at the center of a giant protostar, it starts to give off a ton of energy. This energy helps to balance out the force of gravity, making it kind of like a giant fusion-based star. They would be so bright that each one would look like a small galaxy. Quasi-stars would have a pretty short lifespan, around 7 million years. Just for comparison, our Sun is about 4.5 billion years old, and it's only halfway through its lifetime. But either way, during this short period, the black hole at the center would grow to be about 10,000 times the size of our Sun. Quasi-stars are also thought to be super hot, with temperatures reaching over 17,500 degrees Fahrenheit. But as a quasi-star gets older, it starts to cool down, and its outer layers become see-through. Eventually, it cools down to a temperature of 6,740 degrees Fahrenheit, and at that point, it's curtains for the quasi-star. It can't survive at that temperature, so it just dissipates, leaving behind an intermediate mass black hole. Unfortunately, right now, there's no observational evidence for the existence of quasi-stars. This is because they are thought to have only existed a very, very long time ago. They may have been very massive population 3 stars, which are extremely rare and difficult to detect. It's also very unlikely that any of them would still exist today because of their super short lifetime, only 7 million years. So why do scientists believe that quasi-stars could have existed? Because they're looking for ways to explain how supermassive black holes formed so early in the history of the universe. They're found at the center of most galaxies. But how could these monsters have formed so quickly? After all, it takes a really long time for small black holes to grow into supermassive ones. This is where the idea of quasi-stars comes in. These stars aren't just destructive forces of nature, they're like the black belts in the martial art of gravity. They can bend and twist anything to its will. That's why these stars, if they really existed, had to play a crucial role in the evolution of galaxies. They must have been instrumental in shaping the universe as we know it, so those intermediate-sized black holes that they left behind could eventually turn into supermassive black holes in the centers of galaxies. But we're still yet to solve this cosmic mystery. Detection and study of black hole stars is like trying to find a needle in a haystack, only instead of a needle, it's an invisible and mysterious object, and instead of a haystack, it's the vast expanse of space. But with the help of some pretty cool technology and a lot of brainpower, scientists are getting closer to uncovering the secrets of these celestial giants. Here are some things that can help us in this research. First of all, gravitational waves. They're like ripples in the fabric of space-time caused by the movement of massive objects. Albert Einstein predicted them way back in the 20th century, but they were finally detected only in 2015. We caught them by observing the collision of two black holes. This discovery confirmed that black holes can merge and that they're a powerful source of gravitational waves. Scientists think that by studying these waves, they can learn more about how black holes form and grow. Right now, they use a special space probe, LISA, to study them. By combining the information from LISA with other observations, scientists hope to learn more about these terrifying celestial objects. We can also try to detect quasi-stars by observing the effects of their gravity on nearby objects. And, of course, we can use our technologies, such as X-ray, infrared, and radio telescopes. This allows us to study black holes in various ways and at different stages of their lives. In other words, scientists are working hard to uncover the secrets of these celestial giants. We develop new telescopes, search for primordial black holes, and try to understand the connection between black hole stars and dark matter. And we're making some pretty incredible discoveries, just like with gravitational waves. And when we find out the truth about them, it will become a new page in our scientific history. Well, we've been miscalling Uranus all this time. Astronomers say we should be pronouncing it like urine-ass, not Uranus. I can't say a different stress changes much though. However, things could have been different. Initially, Uranus was supposed to have the majestic, king-like name of George, because astronomers wanted to name it after King George III. In the end, they changed their minds, and now it's the punchline of every joke. If you take the total cost of launching a mission and divide it by the weight of the cargo, you'll see some pretty mind-blowing figures. According to specialists, back in 2016, it used to cost $10,000 to send just 1 pound of cargo into space. But now, prices have gone through the roof. Cygnus spacecraft's cargo costs over $43,000, while SpaceX's new carriers come in at around $27,000 per pound. Remember how hard it is to pay $5 for water at airports? Now, a bottle of water in space would cost somewhere between $9,100 and $43,000, and that's only to have it delivered in space. As for water in space, well, it used to be considered a super rare thing, but in reality, there's water ice all over our solar system, so you don't have to buy those overpriced 43K water bottles. It's hanging out in comets, asteroids, and even in hard-to-see craters on Mercury and the Moon. We're not sure if there's enough water in these places to support colonies of people, though. Mars also has ice at its poles, hiding under its surface dust and frost. Even smaller celestial bodies, like Saturn's moon Enceladus and dwarf planet Ceres, have ice. NASA scientists think there might be a chance of finding life on Jupiter's moon Europa. There may be liquid water beneath its icy shell. Europa, even though it's a lot smaller than Earth, might have an ocean deep enough to hold twice as much water as all the oceans on our planet combined. And in 2009, scientists exploring a massive cloud of gas and dust in the center of our galaxy stumbled upon a fascinating surprise. They found ethyl format within the cloud. This chemical is responsible for the delightful flavor of raspberries and has a rum-like scent. Furthermore, another nearby region is brimming with ethyl alcohol, the same type found in many beverages. In fact, there is enough alcohol in this region to provide every person on Earth with 300,000 pints of beer every day for the next billion years. But believe it or not, but we do have a black hole on Earth. The thing is, creating an in-lab black hole was a sorta indispensable thing to do. Studying black holes in real space remains a distant dream, so it was only possible to create one to experiment with in a lab. A group of scientists in the Netherlands wanted to explore the mysterious Hawking radiation theory proposed by the iconic Stephen Hawking. Using atoms to mimic an event horizon, they orchestrated electrons, causing a surge in temperature that resembled flat space-time. As particles moved through quantum fluctuations, a ring of infrared radiation appeared around the lab-grown black hole, mirroring Hawking's idea. Grown black hole, mirroring Hawking's idea. It may sound insane, but you can totally be allergic to the moon. Long story short, it was the final Apollo mission, and they brought back more rock samples than ever before. Plus, they had the first and only pro-scientist on the moon, Jack Schmitt. He was a geologist, and his rock samples helped scientists learn more about the moon's magnetic field and volcanic history. During the expeditions, it became evident that Jack Schmitt was allergic to moon dust. The gritty, sticky powder clung to his suit and his skin, causing irritation in his sinuses, nose, eyes, and throat for a couple of hours after he took his helmet off. Neutron stars are extremely dense, being basically just a bunch of neutrons squished into a super small space. If you had just a teaspoonful of this stuff, it would weigh more than the entire human population combined. And to match the density of a neutron star, we'd all have to squeeze into a space the size of a sugar cube. No thanks. And when it comes to outer space, we tend to think that Earth and the Moon are pretty close together, but in reality, you could actually squeeze all the other planets of our solar system between Earth and the Moon. The average distance between them is about 384,000 kilometers. If you added up the diameters of the 7 planets, you'd still have some room to spare, about 8,000 kilometers. In 2011, scientists made a groundbreaking discovery of a massive reservoir of water in space. This water, equivalent to 140 trillion times all the water in Earth's oceans, could provide each person on our planet with a planet's worth of water 20,000 times over. This reservoir was located near a massive black hole, drawing in matter and emitting energy, known as a quasar. The water was formed by energy waves colliding hydrogen and oxygen atoms together, and it was found around 12 billion light years away. When Curiosity Mars rover snapped its very first sunset pic in 2015, scientists were practically doing backflips from excitement. Turns out, sunsets on the red planet are anything but red. They're actually a stunning shade of blue. According to NASA, the reason behind this phenomenon is that the dust in Mars's atmosphere is like a magical filter that lets blue light shine through while blocking out those warm tones like yellow, orange, and red. Venus is a slow spinner compared to Earth. It takes this planet 243 days to make a full rotation, and it spins in the opposite direction. But even though Venus takes longer to spin around, it zooms around the sun in just 225 days because it's located so close. So, believe it or not, a year on Venus is actually shorter than its day. I chose 12. You might think that the night sky should be full of stars with no dark spaces at all. This idea is known as Olbers' paradox, named after German astronomer Heinrich Wilhelm Olbers. He thought that if the universe was infinite, unchanging, and timeless, then we should see stars everywhere we look. But it turns out that the universe is not infinite, unchanging, or timeless. Edwin Hubble discovered that the universe is actually expanding, and the leftover radiation from the Big Bang tells us that the universe is about 13.8 billion years old. Think of all the birthday candles. So, the reason we don't see stars in every direction is because some stars are just too far away, or they haven't been around long enough for their light to travel all the way to us. During the Apollo 16 lunar mission, Ken Mattingly, the command module pilot, had a bit of a scare when he realized his wedding ring was missing. The whole crew frantically searched the spacecraft for it, but no luck. Finally, on day 9, while Mattingly was on a spacewalk, the ring was spotted floating out the hatch door. Charles Duke Jr. tried to grab it, but missed. Luckily, it bounced off Mattingly's helmet into Duke's hands. It's cool they found the ring, but there are many other things people left up there. There's even a toothbrush floating around somewhere. Mercury is already the tiniest planet in our solar system, not counting Pluto, of course, and the second densest after Earth, and believe it or not, it's actually shrinking and getting denser. For a long time, scientists thought Earth was the only planet with tectonic activity, but that all changed when the Messenger spacecraft flew by Mercury, giving us a detailed scan of the whole planet. In 2016, Messenger discovered these cool cliff-like formations called fault scarps. Since they're still relatively small, scientists think they're pretty new. suggesting that Mercury is still contracting 4.5 billion years after the solar system began. Around 10 years ago, Italian astronaut Luca Parmitano went through a near-drowning experience during his spacewalk due to a water leak that went unaddressed. Nobody knew how it happened and why Luca ended up having water in his helmet. NASA was investigating the issue for months, but they were unable to determine the exact cause of the water entering Luca's helmet.